going to draw eccentric buckling. Okay. So this is the point. Okay. So now we have a situation when we have buckling. Right. So this is exaggerated. Okay, so we have a situation when we're buckling for centric loading. So our load P is still coming down here. Okay, our load P is still coming down here. And then I'll draw our member over here. So if we put a point over here, and we we select a point over here, point Q, right? So now point Q now has a certain distance away from the applied load. And what was the term that we used? Let me check. I want to be consistent. So this is our Y max, right? This is Y max. So it is when after buckling, if we were to focus at point Q, you have a what? You now have a P over here, right? You have a P now, right? And because the load is generating a moment after buckling, you have P multiplied by Y max over here. Then you have a reaction down here, also P Y max. Okay. Whereas in eccentric buckling, right, it is slightly different. What is this slightly different? So now if we were to draw our centroid, we draw centroid, and then we have our load is offset, right? P, right? And then this is where deformation occur. I mean, so this is our deformation pattern. Okay. You know what? I will do this. Just make sure I can stretch this. Okay, good enough. And then we have our deformation axis. And we know already before that, we have a what? We have a moment over here that is already what? P multiplied by E, right? So now we have a point over here, right? And then we have another Y max at point Q, right? So the moment at point Q now is equal to what? It's equal to P multiplied by E, right? And then we have plus P multiplied by Y max. This is due to the what? This is due to the deflection. I repeat again, this is due to the deflection. Okay, so now you see the difference between centric buckling and eccentric buckling. Okay, so in eccentric buckling, okay, so therefore in eccentric buckling, okay, the stress is equal to P over A bracket 1 plus by EC, okay, EC over R squared, right? Secant, right? 1 over 2 L over R square root P divided by AE, and we close bracket. Okay, so the formula is no more the same. Okay, so why is that? So note for eccentric buckling, okay, the moment at point Q is equal to minus PE minus PY. Okay, and like what I wrote before, this is due to eccentric loading, and this is due to deflection, right? So one, this is before before any deflection. This is due to deflection. Okay, so I'm not going to derive the formula out. Okay, we are just going to apply it. Okay, and the next formula that you have to know is the Y max. Now, if you're interested to derive it, I'll post the notes, okay, on Avenue to Learn, just for you to look at. Okay, last term I derive it. I realize it is long to derive. Just apply the formula. Okay. So Y max. Okay. So the max Y max, or I'm going to write Y max is equal to E. Okay. Multiply by secant square root P over EI, right? And multiply by L over 2. Okay, so this whole thing is in a bracket and minus 1. Okay. So what does all this actually means? Okay. So Y max is the maximum deflection that occur at mid span. Mid span, i.e. L over 2. Okay. And then what terms do we do you're not clear of? If you look at the one on top, P is the applied load. E is what we call our offset distance. C, okay, C is what we define as the point of interest, the distance of interest relative to the centroid. Relative to the centroid. And then we have E. We have, R, sorry, R is our radius of gyration. And then we have our L, which is the length of the column. And then we have E, which you're familiar, is our Young's modulus. I is our second moment of area. Okay. And what else? And that's it. So any more terms that you're not familiar with? We see everything. A is our cross-sectional area. Now, one thing might be you all might not be sure is what do we mean by C? Okay, so if is there any structure that I okay, let's look at hold on, let me pick a structure. This is not very good. Let me see. Okay, that's the only okay. I'll use circle is no good. I'll use this example over here. Yeah, I'll use that example. So what do we mean by C? Okay. So if we were to look on the view, so this is X, Y, and Z, right? And then if we look at our cross-sectional view, if we look at the cross-sectional view now, right? So the cross-sectional view look like this. It's an eye. Okay. And if we were to put our axis in, so this is our X and Y. Okay. So for this case, we do know that based on right by visualization, okay, we know that the green line I draw, these are all our centroid. Okay, so this is our centroid. Okay, means the left and right, the cross section are the same, and this is also the centroid, where the top and bottom is the same. Okay, so depending on how buckling occur, C, okay, C can be this distance over here. Okay, so this is C Y, okay, or it can be this distance. This is our Cx. Okay, so if let's say P is not applied on the centroid because it's eccentric loading, if this is our P, then the distance from here to here, this is our what? This is our E. Are we clear? Okay. So what I'm going to do now is, as I said, this is introduction to eccentric buckling. I'm going to stop over here. Okay. Next week we will do some examples on eccentric buckling. By no means it's by no means it is not necessarily more difficult, but you have to apply the formula. Another thing before I let you go, this value over here, they are all in radians. Okay, these values over here, a lot of times students make mistakes. This you have to calculate them in what? Radians. Not just when you secant the whole thing over here is in radians. Okay, so we make sure you have to put your calculator in radians mode. Okay, with that, I will stop the class now. I'll see you guys next week. Don't forget your homework. Okay.
Hey, Eugene.
Yes.
Last week you posted a list of names that you wanted to meet with.